Hello, good morning. Good morning to all of you. Am I audible? Am I audible to all of you? Please respond. Okay, thank you. So today we would be start with the topic of reception of BPSK or binary phase shift keying technique. So before Deepavali, we have learned how to generate the BPSK signals. Now we have to learn uh, at the receiving side of this signal what process has to be used to recover the actual signal. Okay. So generally, whatever the equation we use to represent the received signal, that is st is equal to bt square root of twice of ps cos 2 omega naught t, that we have already seen in the transmitter end. So the same signal would be going to receive here. Here, if you have to see, one thing is added, I have, that is theta. So theta is nominally fixed phase shift corresponding to the time delay theta upon omega naught. And this time delay depends upon the length of the path from transmitter to receiver, and the phase shift produced by the amplifier in front of the receiver preceding the demodulator. Okay. And the original data bit is recovered in the demodulator output. So we know that in the receiver end, the first the element that we have to be phase the receive signal is demodulator. Okay, but there is some distance the signal has to be covered from the transmitter to receiver, and that distance would be produce the time delay, and that delay is theta upon omega naught. And because of this delay also, and some front end amplifiers before the demodulator, what happens, there is some phase shift would be occur, that is theta is shown in this equation. Okay, so now if you have to be see, everyone please draw this diagram. That is the diagram is used for the BPSK reception of BPSK signal. So you can see here in this particular diagram, uh, up to this section before channel, it is a transmitter end. Then the signal would be passed through the channel, whatever the noise would be added here in the channel, and right side of this channel is nothing but a receiving section, receiver of this BPSK signal. Okay, so you can see here there is a demodulator section where the signal uh, square root of 2 ps bt cos omega naught t plus theta that we have discussed, that would be received by the demodulator input. This is the synchronous demodulator actually. Okay, and the other circuitry that would be, you can see in the receiving end, that is the square law device, band pass filter, frequency divider are mentioned in this particular diagram. So how this receiving would be occurred? So if you have to see here, the demodulation technique usually employed is a synchronous demodulation, and that requires that there are will be available a demodulator, the waveform omega naught t plus theta. So the scheme that is used to generating a carrier at the demodulator end for recovering the baseband signal is shown in this particular diagram. So if you have to do the partition of this diagram, this is the section that I have underlining, that is for the recovery of the carrier, locally recovered the carrier at the receiving end. And this carrier signal would be similar to the baseband signal frequency. So receive signal is, first of all, to recover the carrier, we have to see first this process, how to recover the carrier, and then we have to become for the demodulation section. So first of all, what happens? This signal would be applied to a square law device. Obviously, the received signal having the frequency component omega naught t, and when it would be passed through the square law device, this term would be square, means cos square omega naught t plus theta. Okay, and that would be further written into the mathematical form. I would be discuss this also, and this would be the double the fundamental frequency, twice of omega naught. When you have to be resolve this mathematical equation, it would become cos 2 omega naught t plus theta. So it would be passed through a band pass filter that is tuned to the 2 omega naught. So it would be allow only to pass this frequency component, and DC component would be discarded. And further it would be passed through the frequency divider to obtain the baseband frequency. We have to see through this mathematical equations. This cos square omega naught t plus theta would be further written as per the mathematical formula 1 plus cos 2 omega naught t plus theta upon 2. And here 1 by 2 is a DC component, that is undesired component. It is removed by the band pass filter because it is centered to a frequency that is 2 f naught. That's why it will be only allow the second term, not allow the first term. Okay, so the output of the band pass filter would be cos 2 omega naught t plus theta. After that band pass filter, there is a frequency divider circuit that is composed of a flip-flop and narrow band tuned filter tuned at the frequency of f naught, is used to regenerate the waveform cos omega naught t plus theta. So the synchronous demodulator multiplies the recovered carrier with received signal to generate Bt square root of twice of Ts cos omega naught t plus theta into cos omega naught t plus theta. See, if you have drawn this diagram of the receiver or taken the screenshot, you can refer that diagram to understand this particular part. So you have to see the synchronous demodulator have already one input, that is Bt square root of 2 Ps cos omega naught t plus theta, and other input to it is coming from the recovered carrier, that is cos omega naught t plus theta. So when it would be multiplied with each other, so it would become Bt square root of 2 Ps cos square omega naught t plus theta. Further, we have to be elaborate this particular cos square omega naught t plus theta in to the simplified form. It would be become 1 by 2 plus 1 by 2 cos 2 omega naught t. Again, the frequency component is doubled with respect to the fundamental frequency. Now this signal is applied to the integrator. Okay, now in the receiver circuit, a bit synchronizer is included. This device is able to recognize precisely the moment which correspond to the end of the time interval allocated to one bit and the beginning of the next bit. So at that moment, what happens? It closes the switch SC. Very briefly, just refer the diagram of the receiver. So there is a shown as where is the switch SC. So this at this moment of end of every bit, it closes the switch SC very briefly to discharge the indicator capacitor and leaves the switch SC open during the entire course, ensuring the bit interval. So during the bit interval, it would be open, but at the end of the bit interval, it would be just closed for a very small moment, and that moment it would be discharged the indicating capacitor. So the output of the signal of interest is here, the output of the indicator, and that output would be derived at the end of every bit interval, but immediately before the closing of the switch SC. So the output is made available by the switch SS, which samples the output voltage just prior to the dumping capacitor. So you can see here in the diagram also, in this case, whatever the output of the demodulator or multiplier, that would be applied to a this integrator as well as a bit synchronizer. This bit synchronizer would be uh, turn on and turn off the SC switch at the end of the every bit, and whatever the output of the integrator, okay, this would be uh, available to the user through this switch SS. So what happens when the signal would be come to the input of the integrator, this capacitor would be charged and the integrator output would be available to the switch SS for a very small moment, that is called the bit duration TB, and for that you would be get the actual data that we have used for the transmission section BT. And but at the every end of the every bit, this is the multiple bit information is there. What happens? This switch SC would be closed, and that time whatever the charge stored in this capacitor would be discharged through this path, okay, and that is very small moment. And for again it would be do the same function. The integrator would be produce the output, and bit synchronizer would be synchronize that bit, and you would be get the original message BT. Okay, so this operation would be carried out. So if you have to be do this operation mathematical point of view, so you can assume that the bit interval TB is equal to the duration of an integral number n of the cycles of the carrier of frequency S0. That means n into 2 pi is equal to omega naught TB. So TB is what? Bit interval, and mathematically it is related to the carrier frequency by n into 2 pi is equal to omega naught TB. So n is what? Number of cycles of carrier. Now in this case the output voltage S0 KTB, basically it is S0 T, but T is here replaced by the KTB because we are talking about the bit duration, how much information is coming out from this particular bit duration TB. So at the end of bit interval, that is extending from the previous bit to the next bit, so previous bit is K minus 1 TB to the next bit is the KTB, is can be written as mathematically S0 KTB is equal to B KTB. We are talking about only the bit duration TB that is passing through the integrator. Square root of 2 of PS. Integration limit is K minus 1 TB to KTB 1 upon 2 dt plus, because this signal is available to the input of the integrator, BT square root of 2 PS cos square omega naught T plus theta, and cos square omega naught 2 T would be further expanded as a 1 upon 2 plus 1 upon 2 cos 2 omega naught T plus theta. So here the first term DC component would be there plus BKTB square root of 2 PS, that is again the same limit of the integration 1 upon 2 cos 2 omega naught T plus theta into dt. When you integrate this, you would be found that this sinusoidal term, this is the sinusoidal signal, it would become 0 for the complete cycle of the bit duration. Okay, so this sinusoid would be over whole number of cycles as when we have value 0. So only the first term would be used here to generate the original data, produce the original data format. So it will become BKTB into square root of PS upon 2 into TB. This TB is out of square root. Okay, so this is the required data, that is BT, available to the output of the integrator. Okay, so in this way we have to see that this receiving system would be reproduce the transmitted bit stream BT, and the operation of this bit synchronizer allow us to sense the each bit independently of every other bit. Okay, so this is all about the receiving of the BPSK signal. Now the receiver diagram is also important, and these all equations are very much important, that would be come into the examination. Now we have to come to the another topic, geometrical representation of the BPSK signal. That means we have to learn about the signal space representation. So signal space diagram is a representation of modulated signals using normalized reference signals. Normalized means it is normalization with respect to the energy levels. So the amplitude of the normalized reference signal is generally that is the carrier orthogonal signal. The amplitude of that is square root of 2 upon Ts. Here Ts is what? Symbol duration. That is equivalent to the NTB. TB is the bit duration. And N is what? It will depend upon the number of bits. That is log 2 base to M. If M is equal to 2, means a 2-bit information, it is 1. It is 4-bit information, it is 2. So depending upon the number of bits information is there, the value of N would be changed. Okay. So by using this phenomena, we would be draw the signal space diagram, and in the signal space diagram we generally show the Euclidean distance. What is the Euclidean distance? It is the minimum distance between the two adjacent signal points. What are the two adjacent signal points? One is binary 1, another is binary 0, and each signal having the some energy levels that would be represented on the signal space diagram. So using D or Euclidean distance, the probability of bit error and probability of symbol error for the adjacent coherent digital communication system in the Gaussian noise can be calculated. So that could be mathematical written as what is the value of D, we can easily find out. So the BPSK signal, we know that the mathematical equation of that xt is equal to bt square root of twice of ts into cos 2 pi f naught t or cos omega naught t, whatever. So let us arrange this equation, and we have to multiply and divide the square root of the TB, that is bit duration. So it would be become BT square root of PS TB into square root of 2 upon TB cos 2 pi f naught t, and here the term square root of 2 upon TB and into cos 2 pi f naught t would be nothing but a orthogonal carrier signal, that is phi 1 t. So generally signal space diagram is drawn by the help of orthogonal carrier signal. In one axis phi 1 t, another axis phi 2 t, and then st could be written as Vt is what? Polar NRZ signal. So it is plus minus square root of PSTB phi 1 t. In terms of energy, it is square root of plus minus EB phi 1 t, and Euclidean distance is what? The difference of these two signals. So it is coming as 2 into square root of PSTB or 2 into square root of EB. Okay. So how this would be came? That was very much clear from this signal space diagram. You can see here. You can see one of the signal that is represented the binary 1 or logic 1, that is S1. It is a reference axis. So right hand side of this, that is phi t, orthogonal carrier signal. The amplitude or the distance of the signal from the zero level is square root of EB, and the another signal is S2, that is representing the logic 0 signal point. It is amplitude of minus square root of EB because it is left hand side of the reference axis. So total equivalent distance is what? 2 into square root of EB. Okay. So in this way we have to be draw the signal space diagram as well as the find out the equivalent distance. Okay. On a similar way, you can also draw the power spectrum for BPSK modulated signal. Okay. Just 1 minute. So in the similar way, you can also draw the power spectrum for the BPSK modulated signal. So that is not the part of syllabus, but you can see that how to draw this PSD, power spectral density of the BPSK signal. This is the standardized signal that we have to also come to know about this knowledge. That would be very useful for finding out the any kind of interferences. So you can see this is the generalized A diagram power spectral density of the NRZ polar data, because we are using this NRZ polar signal as an input data bit BT, and this is the resultant BPSK signal. You can see for the binary 1 and binary 0, it would be this would be spreaded on the two side of this reference y-axis. Okay, so one is the positive side, another is the negative side, and both is having the center frequency of f0, and you can see the at the f0 it will be having the maximum power density, that is PS TV upon 2. Okay, and that would be having the bandwidth of the, you can see that is spreaded f0 plus fb here and f0 minus fb here. So from the power spectral density back, actually we have to be find out the bandwidth of the signal. Okay, so in this way you can see the power spectral density of the BPSK signals. Okay, now we have to be moved to the next topic, that is BFSK signal, binary frequency shift keying technique. So in the binary frequency shift keying technique, the binary data waveform DT generates a binary signal by keeping its amplitude and phase constant. Amplitude and phase constant is here. Only the frequency would be varied for the carrier signal. So we have to see how this would be happen. So here we have to be apply two different frequency signals according to the binary symbols. For binary 1, there different frequency, for binary 0, different frequency. So let there be a frequency shift by the omega, and then we can write it as Vt is equal to 1. So SH, that is a signal for the binary level 1, is high level signal SH T square root of 2 PS cos 2 pi f0 plus omega T. Here omega is not phase shift, it is a frequency shift. Remember this. And for binary 0, it is SLT is equal to square root of 2 PS cos 2 pi f0 minus omega T. Okay, so remember these are only frequency shift, not phase shift. Okay, because for each different binary values we have to apply the different frequency levels. Okay, so noted on these equations. Now if you have to be see, there is a increase or decrease in the frequency by the amount of omega from the nominal carrier frequency f0, means the carrier frequency is here, f0 is here. So combining above two equation, you would be got the equation number 3, that is St is equal to square root of 2 PS cos 2 pi f0 t f0 plus dt omega t. So what is the dt is here? Okay, so dt is a nothing but a polar signal. Okay, so that would be representing the binary 1 and binary 0. So binary 1 is represented as a plus 1 volt and binary 0 is represented as a plus minus 1 volt, corresponding to this logic levels 1 and 0. And according to that, you can get for the BFSK signal, the modulated phase shifting technique signals are PST is plus 1 volt for binary 1, and at the same time PL would be 0, as similarly for binary 0, PH would be 0 and PL would be 1. So we will see what is going on actually. PHT and PLT is basically a related to the voltage levels of DT. Okay, so at any time PH or PL is 1, not both at the same time. Okay, because when you have to modulate the signal according to the different frequency for binary 1 and binary 0, So whatever the modulated signal would be generated, that would be uh, either binary 1 or binary 0. CH and PL would be not both 1 or both 0 at the same time. Okay, so there would be generated signal in either frequency FH or FL. Okay, for binary 1 and binary 0, same frequency not be there, always a different frequency. That's why the level of pH and PL would be different. So when dt changes from +1 to -1, pH changes from 1 to 0, and PL would be from 0 to 1. At any time, either pH or PL is 1, but not both, so that the generated signal is either at the frequency FH or FL. If pH is 1, means it is FH frequency. If PL is 1, means it is FL low frequency. Okay, so you can see this is a basic diagram I would try to show. This is the carrier, orthogonal carrier signals are applied to the multiplier, and there is a applied data signal, that is pH is representing here, maybe a 1 or maybe a 0 depending upon the incoming signal, and resultant would be square root of 2 pH cos omega ht. Okay, so if it is a binary 1, so it is omega ht. If it is a binary 0, omega lt would be there, and then it would be added, and finally we have to be generate the BFSK signal. So it is a nominal diagram of the transmitter, but I would be showing you the detailed diagram of the transmitter here in the next slide. So when the symbol 1 is transmitted, carrier frequency would be f0 plus omega upon 2 pi. When the binary 0 is transmitted, when the symbol 0 is transmitted, see here it is not binary 1, it is binary 0. It is symbol 0 is transmitted, then the carrier frequency would be f0 minus omega upon 2 pi. So fh is what? f0 plus omega upon 2 pi, and fl is f0 minus omega upon 2 pi. Okay, depending upon the symbol what we are transmitting, their frequency would be changes. For the binary 1, frequency is increased. For the binary 0, frequency is decreased by the amount of omega upon 2 pi. This is the way that we are generating here. In opposite way also you can use to generate the BFSK signal that we have learned in the practical. Okay, so this is the, please draw this diagram. This is the actual binary FSK transmitter diagram in detailed diagram. So here you can see a input sequence BT is used, and at the same time there is a label shifter pH that would be dependent upon from 1 to 0, it would be varied depending upon the value of dt. Then your label would be increased by the pH, so square root of PS TB PST, and the other end when we have to be receive the binary 0, inverter is used, opposite signal PLT, and then label shifter will be passed to the label shifter, square root of PS TB PL, and both would be come to a multiplier with the different orthogonal carrier signal phi 1t and phi 2t, that is tuned at the different frequency FH and FL. And then further the output of the multiplier would be, or analog switch would be there, square root of 2 PS PST cos 2 pi FT FST, and square root of the 2 PS FPLT cos 2 pi FLT. So it is just representing the binary 1 and 0. At the top end it is a binary 1, it is bottom end is a binary 0 only, and then further it would be passed through an adder where you have to be available a signal that is BFSK signal, that is ST, that is a summation of both of the signal at the both end. Okay, so you can see here from the above diagram, PST is same as the BT, and PLT is inverted version of BT, and PST and PLT are unipolar signal because it is vary only 1 to 0 or 0 to 1. Okay, so the label shifter that converts +1 label to the square root of PSTB, and 0 label is unaffected. At the same time, the output of the label shifter will be square root of PSTB. If output would be square root of PSTB if binary 1 is there. If binary 0, then it is a 0. Okay. Further, there would be passed through these two product modulators. We have seen that, and further it would be passed through the adder. We have to be generate the BFSK signal, binary phase shift king signal. I hope all of you have drawn this diagram and understood the operation of this. It is very simple. It is already defined from this diagram and each and every block. Okay. So in this way, modulated signal are in continuous phase and adder would be at this. This is the signal you can refer here. It is little bit blur, but you can refer this to as when we have got the binary 1, you can see this is a one of the high frequency signal. You can say it is a FH. Okay. And this is your FL. It is low frequency signal. Okay. So according to binary 1, what happens? It would be, you see it will follow the frequency of FH. So this is your PH is here. Okay. And then when it would be passed to the binary 0, so it would follow this FL frequency. So PL is available there. So you can see here FSK modulated signal. This is the FSK modulated signal, last one. So according to the pattern of binary 1 and 0, your frequency of the signal would be modulated. So for binary 1, it is having the higher frequency, that is FH, and for binary 0, it is having the lower frequency, that is FL. Okay. So in this way, this is the representation of the BFSK signal. Okay. Now you can see, if you have to be after the representation of this signal, we have to be learn about the spectrum, power spectral density of the BFSK signal, or the spectrum of the and the bandwidth of the BFSK signal. So as we have seen, the PhD in the BPSK, there's a two discrete lobes are there for binary 1 and binary 0, but here there is no phase shift is there. You can see this is the reference axis. Okay. So there is a bandwidth is 4 times of the FB fundamental frequency, that we have to be see the detailing. First of all, we have to be understood these terms with the help of mathematical equations. If you have to be follow the mathematical equation to define the BFSK signal in terms of PH and PLT, so you would be found that ST would be written as square root of 2 of PS into PST cos 2 pi FT ST. This is the output of adder, plus square root of 2 PS PLT cos 2 pi FLT. Okay, this is the square root of the output of the adder that we have shown in the transmitter circuitry. Okay, so here we have assumed that each of the two signals are of independent, random, and uniformly distributed phase. So each of the signals in this equation looks like the signals, that is square root of 2 PS Vt 2 pi F naught T, which we encountered in the BPSK signal. It is very much similar to that BPSK signal, for which we have already deduced the spectrum. But there is some difference. What is the difference? The difference of, if you have to see the difference between this BPSK signal and BFSK signal. This is the equation of BPSK signal, and this is the equation of the BFSK signal. So if you have to found a difference, so there is a very minor difference of the PH and PL. Means, okay. So in the BPSK signal, Vt is a bipolar. It alternates between the +1 and -1. But in the case of present case, PH and PL are the unipolar signal. It only vary between 0 and 1 level. So when you have to map these two signals, BPSK and BFSK signal, you can rewrite the PH as and PL as 1/2 plus 1/2 P dash HT and 1/2 plus 1/2 P dash LT. Okay. So it is a constant of the bipolar variables. Now here the P dash HT and P dash LT is what? It is a polar signal, that is +1 or -1. Okay. So if it is a P dash HT is the +1, so it will be PHT would become 1. If it is a -1, so it would become 0. So alternatively, automatically you can see that PH and PL would be remains unipolar. But as we are mapping it with respect to the bipolar signal, BPSK signal, so that we have to be define or break this PHT and PLT in this term of P dash HT and P dash LT, where P dash H and P dash L is a bipolar signal. Okay. Now using this terms, now we have to rewrite the equation number, equation ST that we have defined previously, that is square root of 2PS, replace PHT by the 1/2 plus 1/2 P dash HT. Similarly, replace PLT as similarly 1/2 plus 1/2 P dash LT. So further, what happens? It will become HT is equal to equivalent to. Now just separate out the similar kind of the terms. Square root of PS/2 cos 2 pi FHT plus square root of PS/2 cos 2 pi FLT plus square root of PS/2 P dash HT cos 2 pi FHT plus square root of PS/2 P dash LT cos 2 pi FLT. So now there are the 4 terms would be become there, that is reduced from the previous equation of ST. Now in this equation, you can give the equation numbers as well, so that it will be simpler for you to understand. So in this equation that we have the 4 terms, the first 2 terms in the equation would be produce the power spectral density, and which consists of the 2 impulses, one at the FH, another at the FL. Okay. And the last 2 terms in this equation would be last 2 terms. What is the last 2 terms? The last 2, these 2 terms in this equation produce the spectrum which are similar to that of BPSK signal. So one spectrum is located about the FH, another is at the FL. The first 2 term is represent the power spectral density of the BFSK signal, having the 2 impulses, one at the FH, another at the FL, and last 2 terms will be represent the similar to the BPSK signal, that is centered at the frequency FH and FL. Please start to fill up the attendance as well. Only 1 minute is left. Then I hope all of you have written this equation. So further you have to write the ST as square root of PS/2 delta F minus FH plus delta F minus FL, F plus FL. That is, I have told the first 2 terms, that is represent the impulse of the 2 impulses, one at the FH, another at the FL, plus PSTB/2 signum function, sine function of sine phi FH TB upon phi FH TB square plus PSTB/2 sine phi FL TB upon pi FL TB whole square. The individual power spectral density pattern of the 2 terms in this equation, for this case FH minus FL would be become equal to twice of FB. Okay. That we have seen here. So finally you have to be got the bandwidth of BPSK signal is 4 FB. That is twice of the bandwidth of the BPSK. BPSK having the bandwidth of the twice of FB. Otherwise BFSK is 4 of FB. You can see from this power spectral density that we have drawn here. Okay. So for today we have to be stop here. And tomorrow we have to be see the receiving of the BFSK signal and QPSK signaling technique. Okay. Thank you all of you.